Long before headlines focused on rockets, wars, or mega-projects, another story was unfolding behind the scenes. A world where governments pushed engineering beyond normal limits to solve problems most people never see. These machines weren't built to look impressive. They were built because nothing else was powerful enough to do the job. Some reshaped entire landscapes, others carried unimaginable weight, and a few tested ideas that seemed almost impossible at the time. From silent giants crawling across the ground to experimental creations born from urgency and ambition, each project reveals how far innovation can go when scale is no longer a constraint. But not every machine became a lasting success, and some left behind unexpected lessons. What happens when engineering grows so large that practicality, politics, and risk collide? This journey explores the extreme edge of heavy machinery, where size meets strategy and ambition changes the course of history. Crawler Transporter. NASA. Crawler, built to move massive rockets. Before any launch at Kennedy Space Center begins, one of the most important machines in the process starts moving long before ignition. The NASA Crawler Transporter was designed for a specific purpose: transporting fully assembled rockets from the Vehicle Assembly Building to Launch Complex 39 without disassembling them. Instead of redesigning roads or creating smaller rocket sections, engineers developed a massive tracked vehicle capable of carrying an entire launch system safely across several kilometers. Built by the Marion Power Shovel Company and delivered in 1965, the crawler was designed with stability as its main priority. The machine rides on 4 large tracked assemblies that distribute its enormous weight across the ground, allowing it to move slowly while supporting thousands of tons. Hydraulic jacking and leveling systems continually adjust the platform to maintain the rocket's vertical position, even as it ascends the gradual incline toward the launch pad. Measuring more than 40 meters long and weighing several thousand tons, it remains one of the largest self-powered land vehicles ever built. During the Apollo era from 1966 to 1972, the crawler transported multiple Saturn V rockets, including the vehicle used for the Apollo 11 moon landing. Its slow speed, about 1 mile per hour, allowed operators to maintain precise control over balance and movement. Rather than focusing on speed, the design prioritized reliability and accuracy, which were essential when moving such delicate and expensive payloads. After Apollo, NASA upgraded the crawler to support the Space Shuttle program between 1981 and 2011. Structural reinforcements, updated electronics, and modern control systems extended its lifespan far beyond its original mission. Additional modifications completed between 2012 and 2022 prepared it to carry the heavier space launch system for the Artemis program. What makes the crawler transporter unique is not just its size, but its long-term adaptability. While rockets changed dramatically over decades, this ground-based machine continued performing the same critical job, showing how large-scale engineering on Earth plays a major role in making space exploration possible. Bagger 288. Excavator, government mining giant built for extreme earth moving. Across the vast open-pit lignite mines of Germany, one machine came to represent a completely different approach to excavation. Rather than relying on fleets of trucks, loaders, and smaller diggers, engineers developed Bagger 288 as a self-contained system capable of removing enormous layers of earth in a continuous process. Built by the German company Krupp and completed in 1978 for the Rheinbronn mining organization, the machine formed part of a wider effort to maintain steady energy production during a period when lignite coal played a central role in national power generation. Physically, the excavator operates on a scale rarely seen in industrial machinery. Stretching more than 200 meters in length and standing close to 100 meters tall, it moves slowly across the mining site on massive tracked assemblies designed to spread weight evenly over soft terrain. At its front, a rotating bucket wheel cuts into the ground, scooping material non-stop. Instead of pausing to unload, an internal network of conveyor belts transfers soil and rock away from the digging area, allowing the machine to operate almost continuously throughout the day and night. The workflow around Bagger 288 resembles that of a moving industrial facility rather than a single vehicle. Operators monitor digging speed, electrical load, and structural stress from onboard control areas, while teams on the ground coordinate conveyor systems and power supply lines. Because the excavator relies primarily on external electricity, engineers focused on efficiency and endurance rather than rapid movement. Even relocation across the mine requires careful planning, sometimes involving temporary bridges or rerouted infrastructure so the machine can travel safely to its next operating position. Beyond its engineering achievements, Bagger 288 also became part of broader discussions about industrial development and environmental responsibility. Supporters pointed to its ability to streamline operations by replacing multiple smaller machines, reducing logistical complexity within large mining projects. Critics, however, highlighted the scale of landscape transformation associated with surface lignite extraction, raising questions about long-term environmental impact and the future of coal-based energy. Decades after its introduction, the excavator remains a striking example of how government-influenced energy programs pushed heavy machinery toward unprecedented size and specialization. Rather than functioning as a traditional excavator, Bagger 288 represents a shift toward integrated systems designed to reshape entire sections of terrain with consistent, carefully controlled motion. Bagger 293 excavator, one of the largest land machines ever built. By the mid-1990s, engineers were no longer just building larger excavators. They were refining how those machines fit into a wider industrial system. Bagger 293, completed in 1995 by Takraf for the Hambach surface mine, represents this shift. Rather than focusing purely on size, the design emphasized integration with conveyor networks, electrical infrastructure, and long-term production planning inside Germany's tightly regulated energy sector. At first glance, the machine looks similar to earlier bucket wheel giants, but its role is more specialized. Stretching over 200 meters long and standing more than 90 meters tall, Bagger 293 works as a continuous material processing system instead of a traditional excavator. The rotating wheel cuts into the soil while conveyor belts immediately move material away, meaning the machine rarely pauses. Its reliance on external electric power allows stable operation for extended periods, reflecting a design philosophy focused on endurance rather than raw, digging force. The way it is operated also differs from older heavy machinery. Teams monitor stress loads, excavation angles, and terrain conditions from onboard control rooms, treating the excavator more like a mobile industrial plant than a single vehicle. Movement across the mine happens slowly and deliberately, with tracked assemblies spreading weight to prevent ground instability. This gradual repositioning allows mining operations to progress in controlled phases instead of rapid expansion. As debates about coal intensified across Europe in the early 2000s, Bagger 293 became part of a larger discussion about efficiency versus environmental cost. Supporters argued that integrated mega-machines reduced logistical complexity, while critics questioned the long-term impact of large surface mines. Regardless of the controversy, the excavator illustrates a turning point in heavy engineering, a stage where innovation focused less on building the absolute biggest machine and more on creating systems designed to operate continuously within a national energy strategy. Schwerer Gustav railway gun, super heavy artillery built for wartime use. Not every massive military machine changed the outcome of war. Some existed mainly as demonstrations of engineering ambition, and Schwerer Gustav is one of the clearest examples. Developed by the Krupp Company under a German government contract, the railway gun was designed to solve a very specific problem, destroying heavily fortified targets that conventional artillery could not penetrate. Instead of mobility, engineers focused on raw power, creating a weapon so large it had to operate from specially prepared railway tracks. The scale of the system created immediate logistical challenges. The gun's barrel stretched more than 30 meters long, and firing it required shells weighing several tons. Transporting the weapon involved assembling rail lines, positioning support equipment, and coordinating thousands of personnel. Unlike standard artillery units that could relocate quickly, Schwerer Gustav functioned more like a stationary siege platform, built for carefully planned operations rather than fast-moving battles. Its most notable combat use came during the Siege of Sevastopol in 1942, where it targeted fortified Soviet defenses. While the gun demonstrated impressive destructive capability, its limitations became obvious. Preparing the weapon for firing could take weeks, and it required heavy protection from air attacks. As World War II progressed and warfare shifted toward mobility and rapid deployment, commanders began questioning whether such a massive system was practical compared to newer technologies. Operational complexity also made long-term use difficult. Maintaining railway infrastructure, transporting ammunition, and protecting the weapon demanded significant resources that could have been allocated elsewhere. By the later stages of the war, large-scale projects like Schwerer Gustav became harder to sustain as Germany's industrial capacity declined. Historical reports indicate that the gun was eventually destroyed by German forces to prevent capture. Today, Schwerer Gustav is often discussed not just as a weapon, but as a lesson in military engineering priorities. It represents a period when scale and firepower were pushed to extremes, sometimes at the expense of flexibility. Rather than shaping the future of artillery, the railway gun highlighted the limits of oversized weapons in modern warfare, showing how technological ambition can outpace practical battlefield needs. Le Tourneau, TC-497, overland train, military land train for Arctic transport. Instead of building more trucks for icy terrain, the United States Army briefly considered an entirely different idea during the Cold War: a land train long enough to function as a moving supply line. The Le Tourneau TC-497 overland train was created around 1960 as an experimental solution for transporting heavy cargo across remote Arctic regions where roads and airfields were limited. Designed for operations in places like Alaska and Greenland, the machine reflected a period when military planners were willing to test unconventional logistics systems. What made the TC-497 unusual was its distributed power design. Rather than a single engine pulling multiple trailers, gas turbine generators produced electricity that powered motors built directly into the wheels along the train. This setup improved traction on snow and ice while allowing the convoy to stretch hundreds of feet in length. Large, low-pressure tires helped spread the vehicle's weight across frozen ground, and articulated joints between sections allowed gradual turning despite its size. Field tests showed that the overland train could carry significant payloads across terrain that challenged standard military vehicles. Engineers appreciated the modular concept, which allowed cargo units to be added or removed depending on mission needs. However, the same complexity that made the system innovative also created problems. Maintenance requirements were high, fuel use was heavy, and coordinating such a large machine in remote environments proved difficult. At the same time, rapid advances in heavy-lift aviation changed how the military approached Arctic logistics. Aircraft began delivering supplies directly to isolated bases without the need for long ground convoys. Compared to faster and more flexible air transport, a slow-moving land train became less practical. By the mid-1960s, the program was canceled before reaching full operational deployment. Even with its short lifespan, the TC-497 remains one of the most distinctive experimental vehicles of the Cold War era. Rather than representing a failure of engineering, it shows how quickly technological priorities can shift. A machine built for a future that was already being replaced by new developments in military aviation. Antonov AN-225. Mriya, Soviet heavy-lift aircraft for space cargo. Unlike most cargo planes designed for flexibility, the Antonov AN-225 Mriya was built around a single mission, carrying the Soviet Buran space shuttle and Energia rocket components across long distances. Developed during the 1980s by the Antonov Design Bureau under a government contract, the aircraft reflected the scale of late Cold War aerospace projects, where logistics machines had to match the size of the space hardware they supported. From an engineering perspective, the AN-225 was an extreme evolution of the earlier AN-124 transport aircraft. Engineers extended the wings, reinforced the fuselage, and added extra landing gear to handle payloads weighing hundreds of tons. 6 turbofan engines provided the thrust needed to lift the massive structure, while a distinctive twin-tail configuration allowed large external cargo to be mounted along the top of the aircraft without disrupting airflow. When it appeared publicly at the Paris Air Show in 1989, it immediately gained attention as the heaviest aircraft ever to fly. The aircraft's role changed quickly after the collapse of the Soviet Union in 1991. With the Buran program cancelled, the original purpose of the N-225 disappeared, leaving the machine without a clear mission. Instead of being retired, it was later modified for commercial heavy-lift operations. Throughout the late 1990s and early 2000s, the aircraft transported oversized industrial equipment, power generators, and humanitarian aid, taking on jobs that no other cargo plane could manage. Operationally, the An-225 became known for solving logistical problems that would otherwise require disassembly or sea transport. Its large cargo hold and external mounting capability allowed rapid delivery of massive components between continents, turning a machine built for space logistics into a global commercial workhorse. In February 2022, the only completed An-225 was destroyed during fighting near Hostomel Airport in Ukraine. The loss marked the end of an aircraft that had become both an engineering icon and a symbol of heavy-lift aviation. Even after its destruction, the Mriya remains a clear example of how government-driven space programs pushed aircraft design to extremes, creating machines that continued to shape global transport long after their original missions ended. NASA Mobile Launcher Platform, giant rocket platform for Apollo missions. While rockets often receive the most attention during the space race, one of NASA's most important engineering solutions stayed almost completely in the background. The Mobile Launcher Platform was built to solve a logistical problem: how to assemble a massive Saturn V indoors and move it to the launch pad without taking it apart. Instead of transporting rockets in sections, engineers created a reinforced steel base that could carry the entire launch vehicle while also serving as part of the launch infrastructure itself. Structurally, the platform functioned as a mobile launch base. Weighing several thousand tons, it sat on top of the crawler transporter and supported the rocket from assembly through liftoff preparation. Large exhaust openings built into the surface allowed rocket flames to pass through during launch, protecting the structure from extreme heat and pressure. Multiple platforms were constructed so NASA could prepare different missions at the same time, improving efficiency during the peak years of the Apollo program. Between 1967 and 1973, these platforms supported numerous Saturn V missions, including Apollo 11. Unlike many specialized machines that become obsolete after a single project, the mobile launcher platforms were repeatedly modified as NASA's programs evolved. During the Space Shuttle era, engineers added new structural interfaces and upgraded key systems so the same platforms could handle a completely different type of spacecraft. These updates extended their operational life for decades, showing how large-scale infrastructure can adapt alongside changing mission requirements. Operationally, the platform simplified launch preparation by combining transport and support into a single system. Technicians could assemble rockets inside the vehicle assembly building, roll them out slowly to the pad, and begin final checks without transferring the vehicle to another structure. This approach reduced risk and allowed NASA to manage extremely heavy payloads with greater stability. Although rarely highlighted in mission footage, the mobile launcher platform played a central role in enabling large launch vehicles to operate safely and efficiently. Its design demonstrates how some of the most critical innovations in spaceflight were not spacecraft themselves, but the ground systems that made repeated launches possible. M65 Atomic Cannon, nuclear artillery machine from the Cold War. In the early phase of the Cold War, military strategy was shaped by uncertainty about how nuclear weapons would be used on a battlefield. Alongside bombers and emerging missile systems, planners briefly considered adapting traditional artillery to deliver atomic payloads. The result was the M65 atomic cannon, introduced by the United States Army in the early 1950s as a bold experiment that combined familiar gun design with the destructive potential of nuclear technology. Rather than serving as a routine battlefield weapon, the system functioned as a symbol of technological capability during a tense period of global rivalry. The cannon's physical presence alone reflected its unusual purpose. Measuring over 20 meters long and weighing more than 70 tons, it required 2 heavy tractor vehicles to transport it between locations. Moving the weapon was a slow and carefully planned process that involved route preparation, escort teams, and precise positioning before the operation. Unlike conventional artillery designed for rapid deployment, the M65 emphasized stability and controlled firing conditions, reinforcing its role as a strategic demonstration rather than a flexible combat system. Public attention peaked during Operation Upshot Knothole at the Nevada test site in May 1953. During the Grable test, the cannon fired a nuclear artillery shell, proving that atomic weapons could be launched from ground-based guns. The event carried strong political messaging, showcasing engineering innovation while reinforcing the image of military readiness. For a brief moment, the concept suggested that nuclear capability might become integrated into more traditional battlefield platforms. However, the pace of technological change quickly reshaped military thinking. Advances in missile guidance and propulsion offered greater range and faster response times than a massive towed cannon could provide. Missile systems required fewer support crews and could be deployed with greater flexibility, making them more aligned with evolving defense strategies. As these alternatives gained prominence, the practical value of nuclear artillery diminished, and large-scale cannon projects gradually faded from active development. Only a limited number of M65 units were ever produced, and their operational role remained mostly confined to training exercises and demonstrations. By the early 1960s, the concept had largely been replaced by missile-based deterrence, marking the end of an unusual chapter in weapons design. Today, surviving examples of the M65 stand in museums, representing a transitional moment when engineers experimented with merging conventional artillery engineering and nuclear-era innovation before the rapid rise of modern missile technology reshaped the future of warfare. Project Pluto Tory reactor rig, nuclear ramjet test machine for missiles. Some Cold War projects were built to answer a simple question: how far could propulsion technology be pushed if conventional limits were ignored? Project Pluto explored the idea of a nuclear-powered ramjet that could keep a cruise missile flying at high speed for extremely long distances. To study the concept without launching an actual missile, engineers at Lawrence Radiation Laboratory developed the Tory reactor rig, a ground-based test system designed to replicate the airflow and thermal conditions of a nuclear ramjet engine. Unlike a traditional rocket, the Tory reactor did not rely on chemical fuel for thrust. Instead, incoming air passed directly through a nuclear reactor core, where it was heated to extreme temperatures before exiting as high-velocity exhaust. Test versions known as Tory 2A and Tory 2C were constructed in the Nevada desert during the early 1960s. Because of the intense heat and radiation involved, the facility required remote operation, heavy shielding, and specially engineered test structures capable of containing the reactor during operation. From a technical standpoint, the experiments proved that a nuclear ramjet was feasible. The reactor generated enormous noise and power output during testing, demonstrating sustained thrust without conventional fuel consumption. However, the broader concept created serious concerns. The proposed missile design, often called SLAM, would have flown at low altitude while releasing radioactive exhaust, raising environmental and ethical questions alongside strategic debates about escalation during the Cold War. At the same time, rapid advances in intercontinental ballistic missiles began offering faster and more practical nuclear delivery methods. Compared to missile technology, a nuclear-powered cruise system introduced complex risks and limited strategic advantages. By 1964, changing priorities and political pressure led to the cancellation of Project Pluto before any operational deployment could occur. Although the Tory reactor rig never became part of an active weapon system, it remains a clear example of experimental engineering driven by Cold War competition. The project illustrates how governments explored unconventional propulsion ideas at the edge of technological possibility, even when the long-term practicality of those ideas remained uncertain. Big Wind Firefighting Tank, jet-powered machine for oil fire control. Most firefighting equipment is designed to control flames gradually, but the machine known as Big Wind took a completely different approach. Developed by Hungarian engineers in the early 1990s during efforts to extinguish oil well fires in Kuwait after the Gulf War, the vehicle combined military hardware with aviation technology to solve a problem that conventional methods struggled to handle safely. Instead of hoses or foam systems alone, Big Wind used raw engine thrust to overpower massive flames. The design started with a modified T-34 tank chassis, chosen for its durability and ability to move through damaged oil fields. Engineers mounted two MiG-21 jet engines on top of the armored platform, directing their exhaust toward burning wells. Water injected into the jet blast created a dense, high-speed mist that cooled the fire and reduced oxygen at the base of the flames. This allowed crews to approach intense heat zones that would have been too dangerous for standard firefighting vehicles. Operationally, Big Wind worked as part of a coordinated response team. Operators carefully positioned the tank near each burning well, while support crews controlled water flow and monitored heat levels. The combination of armor protection, tracked mobility, and powerful air pressure allowed the machine to extinguish several fires between 1991 and 1992. Its loud engine roar and dramatic visual effect drew global attention, turning the vehicle into a recognizable symbol of unconventional engineering during a crisis. Despite its effectiveness, the concept remained highly specialized. The jet-powered system required significant preparation and was suited mainly for large industrial fires rather than everyday firefighting operations. After the Kuwait missions ended, similar machines were rarely developed, as most emergency agencies focused on more flexible solutions. Even so, Big Wind stands out as an example of problem-driven engineering, a machine created for a specific disaster where traditional tools were not enough. By combining a tank platform with aircraft engines, engineers demonstrated how extreme conditions can lead to unexpected technological solutions. Marion 6360, Captain Excavator, massive electric shovel for mining projects. In the 1960s, some mining projects stopped thinking in terms of individual machines and started designing entire operations around a single giant system. The Marion 6360, known as the Captain, was created in 1965 by the Marion Power Shovel Company for the Central Ohio Coal Company to remove enormous layers of overburden and expose coal seams efficiently. Rather than focusing on mobility or speed, engineers built a dragline that prioritized endurance, reach, and continuous electric operation. One of the machine's defining features was its walking mechanism. Instead of tracks or wheels, hydraulic feet lifted sections of the structure and shifted it forward in slow, controlled steps. This unusual movement allowed the excavator to operate on soft ground without excessive pressure on the surface. Standing more than 60 meters tall and weighing thousands of tons, the Captain carried a massive bucket suspended from a long boom, capable of moving huge volumes of material with each pass. Power supplied through trailing electrical cables enabled extended operation without the limitations of fuel storage. Inside the elevated control cabin, operators managed bucket positioning, swing speed, and excavation patterns while coordinating with ground crews responsible for safety and site planning. Because the machine functioned almost like a moving industrial plant, maintenance teams worked continuously to monitor structural stress and mechanical wear. During its peak years, the dragline symbolized the scale of mid-20th century American mining, where efficiency was measured by how much terrain could be reshaped over long operating cycles. As mining practices evolved toward the late 20th century, economic pressures and environmental regulations began shifting the industry toward different extraction methods. Machines built purely for maximum size and output became less common, and large walking drag lines gradually disappeared from many sites. The Captain's retirement reflected that broader change, a transition from massive single-purpose equipment toward more flexible and regulated mining operations. Few modern projects attempt machines of this scale, making the Marion 6360 a snapshot of a period when industrial engineering focused on building larger and more powerful systems to meet growing energy demand. SLJ 900 Bridge. Launcher. giant machine built to install bridge sections. High-speed rail construction introduced a new style of heavy machinery built not just for lifting, but for assembling infrastructure in motion. The SLJ 900 bridge launcher was developed to install massive precast bridge segments directly along elevated rail lines, allowing engineers to extend long spans without relying on large ground cranes. Designed for large government-backed rail projects, the machine represents a shift toward modular construction, where speed and precision are prioritized to keep major infrastructure projects on schedule. Unlike traditional cranes that operate from the ground, the SLJ 900 moves along the structure it is helping to build. Hydraulic lifting systems raise concrete segments weighing hundreds of tons, while long sliding beams carry each section forward above the track alignment. Once positioned, the launcher carefully lowers the segment into place, aligning it with previously installed sections before advancing to the next position. This step-by-step method allows continuous progress across bridges, rivers, and urban corridors with minimal disruption to traffic below. The bridge launcher functions as part of a larger coordinated workflow. Precast concrete sections are manufactured off-site and delivered ready for installation, reducing the need for extensive fabrication at the construction zone. Operators monitor load balance, hydraulic pressure, and structural alignment from onboard control areas, ensuring each lift remains stable even when working at significant heights. Because the machine advances along completed spans, it reduces the need for temporary support structures and lowers the footprint of heavy equipment on the ground. Visually, the SLJ 900 stands out for its long frame and unusual proportions, often described as insect-like when seen from a distance. Despite its dramatic appearance, its primary role is precision rather than spectacle. Every movement is carefully measured to prevent misalignment, since even small positioning errors could affect the stability of an entire rail section. As high-speed rail networks expanded throughout the 2000s, machines like the SLJ 900 demonstrated how infrastructure construction is evolving toward highly specialized systems. Instead of relying solely on traditional cranes, modern projects increasingly use equipment designed to assemble structures directly in place, turning bridge building into a continuous, carefully controlled process high above the ground. Bertha Tunnel Boring Machine, mega drill built for deep urban tunneling. In the early 2000s, the city of Seattle launched one of the most ambitious infrastructure projects in the United States, replacing the aging Alaskan Way Viaduct with a deep underground highway tunnel. To complete the task beneath a dense urban environment, engineers commissioned a massive tunnel boring machine known as Bertha, named after Seattle Mayor Bertha Knight Landis. Built by Hitachi Zosen under government contract, the machine began operations in 2013 and quickly became one of the largest tunnel boring machines ever constructed for city development. Bertha measured more than 17 meters in diameter and stretched over 100 meters long, making it a true giant beneath the streets. Its rotating cutter head was designed to grind through soil, rock, and debris while hydraulic systems stabilized the tunnel walls behind it. As the machine advanced, workers installed concrete segments to form a permanent tunnel lining, allowing construction to continue safely beneath buildings and waterfront areas. The scale of the project required careful coordination between engineers, city planners, and safety teams to prevent ground movement and protect nearby structures. Despite its advanced design, Bertha faced major challenges early in the project. In December 2013, the machine stopped unexpectedly due to mechanical damage and overheating caused by underground obstacles and component wear. Repairs required years of planning and the construction of a large access pit to reach the cutter head, drawing intense public attention and debate about project costs and timelines. After extensive modifications, Bertha resumed tunneling in 2016 and eventually completed the main excavation by 2017. Although delays and expenses made headlines, the machine ultimately demonstrated how modern engineering can overcome complex urban challenges. The completed tunnel opened to traffic in 2019, replacing an aging elevated roadway with a safer underground route. Today, Bertha remains a symbol of both the risks and rewards of large-scale government infrastructure projects. Its massive size, technical complexity, and dramatic journey beneath Seattle illustrate how heavy machinery plays a crucial role in shaping modern cities while pushing the limits of what is possible beneath the surface. Seawise Giant Dock. Cranes. Heavy shipyard cranes for supertanker construction. Long before the Seawise Giant earned worldwide recognition as the longest ship ever constructed, its creation depended on a complex system of heavy dock cranes operating constantly above the dry dock. During the 1970s, rising global oil demand drove shipbuilders to pursue vessels on an unprecedented scale, forcing engineers to rethink traditional construction methods. Instead of assembling ships piece by piece using smaller equipment, shipyards began relying on massive heavy-lift cranes capable of handling prefabricated steel sections that were far larger and heavier than anything previously attempted. These machines became a central part of government-supported shipbuilding programs, enabling industrial projects that pushed maritime engineering into new territory. Unlike standard port cranes designed to load and unload cargo, shipyard dock cranes were engineered specifically for fabrication precision. Their role was not simply to move material, but to position enormous hull modules with exact alignment so that welding teams could secure them safely. Many of these lifts involved components weighing hundreds of tons, suspended high above partially completed structures. Operators had to account for wind movement, shifting loads, and structural balance, while engineers monitored how each new section affected the stability of the growing vessel. Even small positioning errors could create stress points that would impact the ship's long-term performance. A key element of the Seawise Giant's construction was modular assembly. Large segments of the hull were built separately on land, allowing multiple work crews to fabricate sections simultaneously. Once complete, the dock cranes lifted each module and lowered it into the dry dock, where teams welded the pieces together like parts of a giant industrial puzzle. Naval architects calculated weight distribution and structural forces before every major lift, ensuring that the expanding hull remained properly supported throughout the process. This approach transformed the shipyard into an organized production environment where heavy machinery planning teams and skilled labor worked in constant coordination. Despite their crucial role, the cranes themselves rarely received public attention. The finished supertanker became the symbol of scale, while the machinery that made its construction possible remained largely behind the scenes. Yet, these heavy-lift systems demonstrated how industrial infrastructure often determines whether ambitious engineering projects can succeed. Modern shipyards continue to use advanced cranes inspired by these earlier designs, proving that even the largest vessels begin not in open water, but as massive steel structures carefully lifted, aligned, and assembled by powerful machines on land.